So now that you know a little bit more about the forces that are at work on the inside of an atom, it's really time to start talking about the different types of bonding. Before we do that, just a little piece of background. I want to make sure that you understand what this picture actually looks like. This is a picture of what we think an atom may actually look like. We would actually call this image a probability cloud. It's showing you the probable locations of the electrons around the outside of an atom. Sometimes you'll actually see it pictured something more like this, where you have a shaded area around the nucleus, which shows you where a lot of the electrons spend a lot of their time. So I just want to make sure that you have that in your head as we move forward, because it shows how the electrons are actually moving around that nucleus. That's going to be super duper important. So sometimes when two atoms come together, they can bond, but there's a whole bunch of different types of bonds that can actually occur. A bond is a force that holds those two atoms together. That's an important definition and one you should definitely have down in your notes. Now I'm going to show you three different pictures, and I want you to keep in mind that probability cloud, where the electrons probably are around the nucleus, because there's three important images here to take a look at. Now what you're seeing here, the black dots, are the nuclei on the inside of individual atoms. That means in each one of these pictures, there are two atoms, but the electrons are not being handled the same. Now, you may have seen pictures similar to this last year in biology, specifically in the process of mitosis. Don't these pictures look pretty similar to like the end phases of mitosis? Kind of interesting, almost like those two cells pulling apart. That might actually not be a bad idea to have that in the back of your mind as we talk about what we're going to talk about here. So we have three incredibly different types of bonds. So what makes these so terribly different? Well, let's take a look at the left-hand image first. I think that's probably the easiest to understand. You'll notice that the electron cloud is pretty evenly distributed between those two nuclei. So we would say that there's an equal pull on the electrons on the part of both of those nuclei, on the part of both of those electrons. And what creates that is a very low difference in the electronegativities. So in other words, both of those atoms have approximately the same-ish electronegativity. The middle picture is a little bit different. Now you can see that the electron cloud isn't being shared as equally. There's a slight unevenness to that pull there. And what creates that is a larger difference in the electronegativity. One atom has a greater electronegativity and one atom has a lower electronegativity. Now, one way that we would actually designate that is with a very special type of symbol. And it looks a little thing like this. It almost looks like a little melting half note or like a melting D, like a lowercase d. This is actually a Greek letter. It's the lowercase delta. And what little lowercase delta actually means is a slight shift in. That means that there is a slight shift in where the electrons are located around these nuclei. We use the lowercase d delta with a minus symbol to indicate where the electrons are spending more of their time. Now remember that electrons are negatively charged, so lowercase d delta with a negative sign means that the electrons are shifting toward that one atom. And that a lowercase d delta with a plus sign means that the electrons are spending less time on that atom. That's usually where we have the lower electronegativity number. Now there's a second way that you can denote this, and it's with a very fancy kind of arrow. Now we do a little arrow with a hash mark on the one side of it that looks kind of like a plus sign. Now notice that it's drawn from one nuclei toward the other nuclei, and it is in the direction of pointing toward the higher electronegativity. It's supposed to point toward the direction that the electrons are actually being pulled in. This arrow is called a dipole arrow. We use them very frequently in chemistry, so I think it's very noteworthy. You might want to draw a few into your notebook. It's a symbol that you'll see me using quite frequently throughout the year. Finally, our third image. You'll notice that the electrons now have completely pulled away. There's nothing in between these two nuclei, nothing being shared at all. Now, this is caused by a very large difference in the electronegativity. Now, just like we did with the middle image, it's important to denote where the electrons are spending more of their time. But our symbol here is going to be a little bit different. Now, you can tell where we have less electron density. It looks like a smaller bubble around our nucleus. That's the atom that has the lower electronegativity. There's less of a pull of the electrons by that particular atom. And that the atom with the larger bubble around it, the larger probability cloud of electrons, would have the higher electronegativity. The other important thing to denote, that when those bubbles are actually smushed together, that indicates a scenario where the electrons are being shared. And that's a really important thing to note. Two of these types of bonds actually have electrons that are shared. One is equally shared, one is unequally shared. And then the third type, there's nothing being shared at all. It's almost as if the electrons are stolen from one atom and given to the other. Now, like I said, the symbolage here is going to actually change. Because the electrons are officially taken from one atom and given to another, we're going to, instead of having that little low melting D saying there's a slight shift in the electrons, now the electrons have completely moved. These atoms officially have a charge now. We can actually just go ahead and call the one positively charged and the one negatively charged. Typically, there's a larger field of electrons around the thing that's minus, and then a smaller field of electrons around the thing that is plus. And the symbol behind that is also going to be slightly different as well. The capital D in the Greek alphabet is also called delta, and you can see that it just looks like a big old fancy triangle. You may have seen a math teacher using this symbol. It means difference in, and typically we'll just subtract the values that we would find for these to create this difference in. All right, now let's review these three types of bonds just one more time. So our first type of bond, instead of actually going through and saying these qualitative terms, equal pull an electron with a low electronegativity difference, that's very qualitative. Let's put something quantitative to it now. Generally speaking, the guideline states that any electronegativity difference, which is between 0 and 0.5, will give you something called a nonpolar covalent bond, which this image to the right is exemplifying. Now again, this is where you have a perfect sharing of electrons. Nonpolar means not pulled. The electrons are not pulled to one side or the other. And covalent means that the electrons are shared. Now to the image in the right. This one says slight unequal pulling of the electrons. Well, what that means is that there has to be a greater difference in that electronegativity. Let's put some numbers to this now. We say that the electronegativity difference between these two atoms should be somewhere in the ballpark of about 0.5 all the way up to about 1.7. Now, don't all go out and Google this and yell at me because my numbers are slightly different than what you might find on the internet. It really depends on what text and what source you're using. I've seen the numbers go as low as 0.3 and as high as 2.0 for the difference here. This is just a guideline for right now. I'm not going to give you any questions that are right on the dot here of these numbers because that would just be unfair. But again, this is a guideline. Now, when you're in this range and you have this slight unequal sharing in these electrons, we would call this a polar covalent bond. Polar means that the electrons are actually pulled to one side, yet covalent means that they're still shared. Now the third and final type of bond. We have this great unequal shifting of electrons. Nothing is being shared. Do you think we're going to use that word covalent anymore? No, because covalent means shared. So let's come up with something else. That number, the difference in electronegativity between these two atoms, has to be above 1.7. We call this an ionic bond, and this is where the electrons are stolen. All right. So how am I going to be able to tell what type of bonding is really between these two atoms? I have a couple examples here to show you. For example, what type of bonding might be in the molecule carbon monoxide? We'll learn how to name them in a little bit, but between C and O. First thing that I'm going to do is go to my handy dandy periodic table and look both of these elements up. But what I'm looking for this time is their electronegativity values. So here's carbon and here's oxygen. I'm going to write down those two values, 3.5 and 2.5, and simply subtract them. I find that the difference is about 1.0, and if you can remember the differences from before, 1.0 puts me in the range of having a polar covalent bond. So I would expect carbon and oxygen to share electrons, but not equally. Well, what about this lovely little molecule, CH4? You might be wondering, oh my goodness, what's that 4 thing all about? Well, that little 4 thing is called a subscript. And a subscript is used to tell us how many of that particular atom was in the inside of that molecule. Subscripts always follow that letter and will tell us how many of that letter are in the molecule. In this case, it means that I would have 4 hydrogens. Now, I'm going to take a moment here to make sure that you understand that a bond only connects 2 atoms. So in this particular molecule, I'm looking at a bond only between 1 carbon and 1 hydrogen. In this molecule, I would have several bonds that hold several of my atoms together. Anytime that you have more than 3 atoms, I should say, there should be more than 1 bond. So 1 carbon and 1 hydrogen. Again, you're going to go to the handy-dandy periodic table and look up both of their electronegativity values. Write them down and subtract them. And here you'll find that the difference in electronegativity is actually about 0.4, and that should translate to a non-polar covalent bond. So now it's time for you to practice, and I want to make sure that you have a way of checking your work. So I came up with a couple of example problems for you here. What I'd like you to do is to just push pause, see if you can work out the electronegativity differences and what type of bond each one of these would have. And then when you're ready, go ahead and push play, and I'll have the answers ready for you. All right, so now that you've had some time to work out what type of bonding is between each of these lovely sets of atoms, it's time to reveal the answers. Are you ready? Drum roll, please. Ta-da! I hope you did well. If not, you might want to rewind the video and start again, or pop me an email and I'd be happy to help.